right, our next presenter is Kyle Eastman. Kyle is an economic geologist with the Montana Bureau of Mines and Geology and conducts field-based critical mineral prospective studies. Kyle's research interests include guess I can be loud, magmatic hydrothermal ore systems, and he's worked on porphyry epithermal skarn projects in Australia, Indonesia, and South America. Kyle is a passionate mineral collector and enjoys mountain biking and rock climbing. Please welcome Kyle.
Thank you. All right. I think I'll walk around a little bit and try not to trip over this. So I'm with the Montana Bureau of Mines and Geology, and we are a non-regulatory state agency. We're also a department of Montana Tech. And recently, within the past few years, we've been receiving USGS funding to generate pre-competitive geoscience data that's airborne geophysics as well as geological mapping and geochemical reconnaissance, and have lots of collaborators from all over who've been coming in to help us work on these projects. All right, so what is the Earth MRI program? Earth MRI is Earth Mapping Resources Initiative. And so this was a program that was started under the first Trump administration, and then it was given a $300 million boost by the bipartisan infrastructure law by the Biden administration, so it enjoys somewhat bipartisan support. And the goal is to generate this pre-competitive data that will help us find ore deposits, find critical minerals, but also what we're doing is workforce development and trying to train the next generation of economic geologists at Montana Tech and at other universities in the Montana University system. All right, so why do we care? Why are we generating this pre-competitive geoscience data? And here's an example from Australia, and they dump a lot of money into their resources sector from the federal and state governments, and then they have reports that are produced to demonstrate the value of doing that. And in this case, they've been able to show in 2021 to 2022 that they invested $70 million and they turned that into a $70 billion value add for the resources sector. And that includes things such as tax revenues, such as jobs, and you can see all of that there. So it's certainly worth doing and important for the entire mining value chain, as demonstrated by Australia, and not too bad, 3.5% of their GDP right there. Okay, so what are we doing here in Montana in terms of pre-competitive Earth MRI data? The blue polygons are airborne geophysical surveys that have been flown and have been contracted. And so there's our 2022 survey. Oops, sorry, I need the laser here. There's our 2022 survey that is publicly available. This is our 2023 survey that is about to be publicly available, but I'll show you a little bit of a sneak peek here in a minute. And then we're working to fill out what was mentioned earlier by Zachary is the Montana-Idaho Porphyry Belt, right? So we're working within this broader region to try and find magmatic hydrothermal ore deposits, also covering the Sheep Creek rare earth element projects down there along the Montana-Idaho border, the Phosphorus Formation. I believe Adrian talked about that within the past couple days here at this conference. And then we're following up our geophysical surveys with mapping projects. And so we're doing mapping in geochemistry on the eastern margin of the Boulder Batholith, and we have a new project that's going to be starting up this year in the Eastern Pioneers. All right, so there's two types of airborne geophysical data that we're collecting. The first type that I'm going to talk about is and I'm probably going to talk more about this radiometric data today, but you can see that this is our 3-channel potassium, thorium, uranium data collected at 200-meter flight line spacing with a helicopter. And so there's our pre-approved by the USGS Montana-Idaho Porphyry Belt. So over the coming years, we're going to be trying to color within the lines here and fill out, there's our magnetics, fill out this area here in the dashed polygon that extends out into Idaho as well. And it'll be a really interesting transect of geophysical coverage across this part of the Rocky Mountains. So there's our red, blue, green image for potassium, thorium, uranium of the Boulder Batholith, which is a bright white feature in our airborne radiometrics because it has high values of all three, relatively radioactive material. That's mostly the butte granite there that we're seeing. And then there's the magnetic data for the same area. And so you can see lots of magnetic features, particularly around the boundary with the boulder batholith. And you can see our project area polygons, our mapping areas. So in the subsequent slides, we're going to be zooming in and thinking about some of those projects, mapping and geochemistry projects that we're working on along the eastern margin of the boulder batholith. And why do we care about the boulder batholith? Well, if you've ever looked at a map of abandoned mine sites in Montana, you know that there's thousands and thousands of abandoned or inactive mine features, in addition to the Tier 1 Butte system, Golden Sunlight, and lots of other well-mineralized systems in the area. So the idea here is to identify which of these are associated with critical minerals, how that's occurring, and so that's sort of at the small scale, at the hand sample scale, and then working our way up, working across scales to the district and deposit scale, figuring out if there are hydrothermal alteration anomalies, maybe actinolite orbs, for example, that could be associated with our critical minerals, and then relating that to our new geophysical and geochemical survey data that we're collecting to hopefully develop some high-quality regional interpretations that you all as explorers and miners can go forward and use, hopefully to find that Tier 1 project, right? Okay, ore deposits in the boulder batholith. This here is a heat map that is showing the density of abandoned and inactive mine features. And so it really highlights some interesting spots and helped us identify where we wanted to go with our geophysical surveys and with our boots on the ground mapping and geochemical sampling. There's a variety of different deposit types that we see in the boulder batholith region, and that spans everything from the purely magmatic end, where we see little pegmatites, all the way through what we call the magmatic hydrothermal transition. We have magmas that are intruding and releasing volatiles into the surrounding rock, and that creates mineralization, veins, these polymetallic lodes, porphyry deposits. We have skarns, as was talked about recently, the Madison property, and then we have our more distal hydrothermal carbonate replacement deposits where we're less connected to our magmatic source of fluids. Lots of these deposits have sphalerite, and sphalerite is a classic garbage mineral in the sense that it soaks up all sorts of goodies, and many of those goodies are on the critical minerals list. And so zinc obviously is on the criticals list, but also indium, gallium, germanium, and tungsten are all substituted into sphalerite. And so wherever we find sphalerite, or wherever we find zinc mineralization in the boulder batholith region, we're likely to find some of these goodies that China could be putting on the embargo list. All right, so here's the periodic table. Colored up with the orange elements are the 2022 critical minerals list from the USGS. And of course, critical minerals is always a bit of a moving target, and we might be getting a new list this year, and so this will change, and there might be new priorities that come up. But for the boulder batholith region, what's highlighted in red there are the elements that we're likely to find and are likely to be in elevated concentrations. So in addition to everything that we have in our polymetallic veins and our porphyries, copper, lead, zinc, silver, antimony, those sorts of things, we're seeing lots of other elements. So these are the suite of chalcophile elements here on the right that are substituting in to sphalerite, but we also see manganese, we also see vanadium, tungsten, and barium enriched in the boulder batholith region. And here's an example of sphalerite in the Anaconda Research Collection that we house at MBMG. And that sphalerite is fluorescent red under long wave UV light. That's a $20 light that you can buy on Amazon, 365 nanometer wavelength. And if you're working on a project that has sphalerite, look at it with one of these lights. If it fluoresces bright colors, red, orange, sometimes green or blue, that indicates that it's elevated in these trace metals here that we see associated with zinc and with sphalerite. Okay, so zooming in a bit on our mapping and geochemistry projects, we're very interested in the eastern margin of the boulder batholith. That's a historically well mineralized and lots of historic mine features in that area. And we have a number of Earth MRI and EDMAP quad mapping projects that are in this area. So Elkhorn project there, that was a project that was completed in 2022. We have active mapping at the Giant Hill and Radersburg quads, and there's an EdMap project that's a collaboration with MSU that's happening at the Crow Creek Falls quad. So that's the geologic map on the left side there, 100K mapping. And then on the right side, that shows our airborne radiometric data. And so what we can see there, there's the boulder batholith, that's this bright white up in the upper left-hand corner there. And the various sort of pinks and purples that wrap around here are the Elkhorn Mountain volcanics. And the Elkhorn Mountain volcanics, like George mentioned, we want to find that Mount Pinatubo that didn't erupt, right? So we're looking in these volcanic rocks for alteration and mineralization and try and identify vectors that can lead us towards hopefully mineralization. All right, so we've been doing a lot of sampling, and I'll take you through a few slides in the latter half of this talk that deal with how we've begun to interpret the whole rock geochemistry that comes out of these sample sites. So you can see we have sampling in the Elkhorn Quad and the Radersburg and Giant Hill quads, and there's two main mineralized systems: the Diamond Hill Porphyry Skarn system in the Giant Hill Quad, and the Ohio Keating system, which is also known as the Radersburg Porphyry in the Radersburg Quad. So let's have a quick look at the Elkhorn Mountain volcanics. George mentioned the green rock environment, and so there's tons of epidote and chlorite, a little bit of actinolite in places. Haven't seen any orbs at Radersburg or Giant Hill, but we have seen some at Elkhorn. And in that case, the orbs are within a couple hundred meters of a known porphyry at Elkhorn. So it's good to see these things holding up throughout the region. But we can see lots of epidote and chlorite. We see lots of red hematite. So these are altered volcanic rocks, and we want to figure out how to navigate in a lot of these altered volcanic rocks. And sometimes they are completely blasted with white micas, hydrothermal potassium feldspar, sulfides, that sort of thing. So here's an example from the Radersburg area where we have, this was either Elkhorn Mountain volcanics or a related shallow intrusion, and it's been altered and mineralized. It's got lots of sulfides, pyrrhotite in there. You can see relic feldspar sites in there in this SEM element map, and then all the pink stuff is hydrothermal potassium feldspar and some amount of sericite or white mica that's been replacing those feldspars as well. All right, so taking all that whole rock geochemical data that we've been collecting, we can begin to classify that up and determine what type of hydrothermal alteration we're dealing with in these volcanic and shallow intrusive igneous rocks. So this plot here is used to think about what is happening to feldspars. And feldspars are very common, and they are often a target for hydrothermal fluids that are going to come through the rock, and they're going to alter these feldspars. So in this plot, we are comparing the potassium to aluminum ratio on the y-axis, the sodium to aluminum ratio on the x-axis. So albite, sodium feldspar is over there. Potassium feldspar orthoclase is up there. This is our alkali feldspar tie line. And this circle here with all these gray dots is where we see normal, unaltered, fresh igneous rocks most of the time. So there's a reference node for basalt. There's a reference node for rhyolite. And this in here is our Elkhorn Mountain volcanics for the most part in there. And so when we see increases in potassium, I've classified those points as potassic alteration, excess potassium feldspar, like what we might see in a porphyry copper deposit. And then here, this is the muscovite node, about 0.3 potassium to aluminum. And so points that have started over here and drifted over towards that muscovite node, that's probably sericitic alteration. So we can use this plot to identify what type of alteration has happened to our feldspars, and then classify that up and see if it makes any sense in the context of our airborne geophysical surveys. So see if it works, right? So I've classified those points in terms of potassic, sericitic, argillic, various alteration classes. And now what I'm doing is I'm comparing that to the airborne radiometric data. So what we did is we sampled those pixels from the airborne radiometric data from the exact locations where the samples were collected. And hopefully we got a representative sample that came from within that pixel in the airborne radiometric data. So on this side, this ternary diagram is comparing potassium to thorium and uranium in the airborne radiometrics. And this is doing the same thing, but for the whole rock geochemistry data that came from those pixels, that sample site. And so what the takeaway message here is there seems to be more variability between our potassium and thorium, and especially with many of these altered rocks that have either that potassic or that cerasitic alteration. So this then suggests that we can use this potassium to thorium ratio in our airborne radiometrics to identify hydrothermal alteration that might be associated with a porphyry copper deposit. So let's do that, right? So here's a few images of the Radersburg porphyry area. There's the town of Radersburg there, and we have our geologic map. We have our 3-channel potassium, thorium, uranium showing us this red blob, meaning there's tons of potassium in the area. We know there's hydrothermal alteration. We've been out there on the ground and we've sampled it. We also have our airborne magnetics that we're using too in the area. And we can do a little bit of raster math to come up with that potassium to thorium ratio. And sure enough, right there, bright red spot in the potassium thorium ratio indicating excess potassium. And we've confirmed that with our whole rock geochemistry data. So go put your drill rig right there. What are you guys waiting for? All right, so switching gears a little bit, we talked about classifying the hydrothermal alteration and relating that to the airborne radiometrics. Now let's think about our whole rock geochemistry in terms of porphyry copper prospectivity and the magmatic processes, as George has been talking about, the magmatic processes that might lead to the generation of a porphyry copper deposit. And so it's the vanadium-scandium ratio that seems to be, and this is well documented from porphyry copper deposits around the world, seems to be related to hydrous magmas that can fractionate hornblende. And so that the vanadium is going to be going into magnetite, and the scandium is going to be going into hornblende. And so if you have a magma that is fractionating hornblende, you must have about 4% or greater water in that melt, and that means that you can be moving some metals around, and you might be making a porphyry copper deposit. And I'm using scandium here as a stand-in for silica. A lot of industry data sets, you might not get your major elements. You might only get a handful of metals. Scandium might be one of them. And so you're actually tracking our fractionation here from more mafic rocks to more silicic rocks. And then we see a trend up this direction where we see hornblende fractionation, and anything that's going down in this magnetite fractionation direction, that's probably not going to be of interest for our porphyry copper deposit prospectivity. So let's take a look at some of the rocks that we're seeing in this area. Here's a lava porphyritic andesite, part of the lower Elkhorn Mountain volcanics, and it's sitting right about there, more or less where you'd expect it to. And we got an argon age on hornblende that's about 83 million years. So here's some rocks that are much younger, still waiting on an age on these, but these are our tertiary volcanics they're much younger than a lot of our mineralized rocks that we're seeing out in the Radersburg area. And the vanadium to scandium ratio that we're seeing here really indicates that these are not prospective. These are not the rocks you want to be looking in for porphyry copper deposits. They're probably fractionating magnetite. Now here's an interesting one. Doesn't look all that impressive actually, but it's this finely porphyritic dike that's in the Radersburg area, returned an age of about 76 million years, and that's sitting squarely within our hornblende fractionation field where we might have a hydrous magma that's capable of exsolving volatiles and creating a porphyry copper deposit. So that's interesting. This is telling us that we're within the right neighborhood. We should be looking for porphyry copper deposits here. Well, wouldn't you know, there is a porphyry copper deposit in the area. There's the Diamond Hill porphyry, and this one has an absurdly high vanadium to scandium ratio, but there's a caveat here, in that this thing is altered and mineralized. It's full of magnetite. That magnetite has got lots of this hydrothermal magnetite in this case that formed late in the crystallization and the hydrothermal alteration of this system, and so it's going to have excess vanadium in it anyway. So anyway, it's good to see it up there, and that thing got dated at 77 million years. That's uranium lead age. So to wrap things up here, let's try and put it all in the context of the timeline of geologic events that have happened in this part of Montana. And starting around 100 million years ago, We had the Western Interior Seaway. This is the waning stages of that interior sea. And so we're going from black shales to conglomerates of the Slim Sam Formation. And then we have the eruption of the lower Elkhorn Mountain volcanics. This is arc magmatism in the late Cretaceous. Those lahars and pyroclastic flows and lavas were erupted out as part of these arc magmas. And then there's also lots of intrusions that are related to that. And we can see that there's mineralization associated with that event. This is the Pinatubo, right? Hopefully, the Pinatubo that did not erupt. And then there's some gap in time here. We have the Lowland Creek volcanics. We see Montana tunnels associated with that. And then we have the Renova Formation. And so this is our timeline, and we see golden sunlight mineralization. We see butte mineralization. We see Montana tunnels in there. And then from our quads that we mapped out there in the eastern margin of the Boulder Batholith, we have a number of different ages that are all right in this sort of 75 to 85 million year range. Lots of different stocks. Lots of them have this vanadium-scandium ratio that shows that we're prospective for porphyry copper deposits. So it's all telling us we have protracted magmatism that could be related to mineralization. We can tie it to our airborne geophysical signals. So go have fun and find a porphyry copper deposit. And to wrap things up here, we got lots of new data. We can use our whole rock geochemistry to assess our critical minerals content, our magmatic prospectivity, our hydrothermal alteration. And while we're doing this at the Montana Bureau of Mines Geology, we're also engaged in workforce development. So we're collaborating with students and researchers throughout the Montana University system. Lots of acknowledgements there. Lots of Bureau folks have helped. Montana Tech, MSU, Silverbow Mining, Clementine, George is here today, Montana Resources, Celerity, John Childs is somewhere here today, and lots of USGS folks as well. And so this is the USGS Boulder Batholith team out there looking at maps with George Brimhall, the Clementine project. So thank you. Take any questions. Must be close to lunchtime. Yeah, that's a great question. And so with our airborne geophysics, it's looking like we're going to head up into the big belts and little belts and head to the northeast within that Montana-Idaho porphyry belt. So that's where we're going with geophysics. And we typically chase our geophysics with our geological mapping projects. And so we've kind of extended from the Boulder Batholith to the southwest, and we're starting up a Pioneers project pretty soon. And then, after that, we're probably going to be heading up and chasing those new geophysics starting in, 2027, 2028. We'll be headed up there to the northeast. Yeah.